Hi everyone, so this is a review for Chapter 8 revision quiz on Set 3. So there's 26 responses. Okay, we discussed question 4 and question 5. Okay, more than 10 people request help for these two questions. So let's look at the first question. Question 4. You have a ring, a disc, and a sphere. And they are all uniform rigid bodies. Means by the density of the object everywhere is the same. The mass of the object for every unit volume across the whole body is the same. The density is constant for the whole rigid body. So these three rigid bodies have the same mass and the same radius. So now the question asks, which one has the smallest I? Okay, now if you see the I and you don't know what it means, right, then it's quite dangerous because question can ask things like this. Okay, they give you the symbol but they didn't really elaborate what does it mean. So I here means the moment of inertia. So we are looking which rigid body here has the smallest moment of inertia. So let me zoom out a bit. So here are the three objects that I have, and be very careful and remind yourself always that these three objects here have the same mass and they have the same radius, so that will make our comparison more consistent. Okay, so if you can recall our moment of inertia, the formula, the general formula, if you have a lot of particles, then it will be sum of mr square. So if mass increase, then your moment of inertia will increase. But if you look at these three shapes over here, they all have the same mass. So for 1, 2, 3, same mass. So what they substitute is, so the m will not affect things. So what we care about right now is the r. So when I say mi ri square, what does it mean is, for let's say for this unit little mass here, what is its distance from the axis of rotation? Okay, so you do this for all the particles in the sphere, you get their mass, then you get their distance from the axis of rotation. So doing this, you add them all up and you get your moment of inertia. So what does this thing means is, if your distance is greater from the axis of rotation, means by if the mass is far away from the axis of rotation, you get a greater moment of inertia. If you can't recall what does this concept mean, probably you can rewatch one of my video where I demonstrate moment of inertia. Okay, so now we care about how the mass is being distributed. So let's look at case 1 and compare with case 2. Okay, remember this ring over here have the same mass with the disc over here. So what's the difference between the ring and the disc is that for this disc, if you push all the mass in the center, to the rim, to the circumference, like if you imagine this like a dough, okay, like the dough that you use to make bread, the tepung gandum, the dough, right? You imagine you push all your dough to form a donut shape. Okay, so now all your mass is being concentrated on the outside. Okay, from a roti canai shape, you make it into a donut shape. So if you don't take out any dough from the table, so you keep the amount of dough the same, so it means by outside here will be very massive, then inside will be nothing. For here, everywhere will be almost the same. Everywhere will be the same mass. But here, outside will be very heavy, then the center will be nothing. So if you concentrate the mass at somewhere which is far away from the center, then your R will be greatly increased. Therefore, your moment of inertia will increase. Therefore, the conclusion that I can make is the moment of inertia of the ring will be greater than the moment of inertia of the disk. Okay, so that's how I compare. Now, if I compare between disk and sphere, then it's like you can be changing. It's like if you have a roti canai shaped dough, then you squeeze it up to form a sphere. Okay, then you see that the sphere will have a lower density, but you push all the mass inside here, you push it near towards the axis of rotation. Actually, you're decreasing the density, but you're pushing the mass nearer to the axis of rotation. I'm not sure whether I can draw it or not, but if this is your disk, right, before that your disk is that dense. But what you can think of is you reduce the density of the mass, but in terms you make it 3D. So you share the mass up here instead, and you share the mass down here. Okay, instead of pressing everything into a disk, you make the density smaller, you make it less dense. So you're changing from a wood disk to a polystyrene sphere, provided that the wood disk and the polystyrene sphere have the same mass. But now more mass are near the center right now. Now you have this much mass that is near the center. The whole cylinder of mass is near the center. But before this, if you're comparing with this just now, there's only this much mass that is near the center. This is just a disk only. Okay, this is just a disk. But this one, you can see it's a whole cylinder that is near the axis of rotation. So in that case, you can see that there are more mass that is near the axis of rotation. So if more mass are near the axis of rotation, then you can think of this R as being the effective R, you can think of it as decrease. So more mass are near the center, so you can think of the effective mass decrease. So in that case, you can actually think that this moment of inertia will decrease, because you can think of more of this M will have smaller R. Many M will have smaller R. A little bit of M will have great R. Whereas for this one, a little bit of M have small r, a lot of M has big R. So it's hard to imagine. If you probably need to play with some plasticine to get the idea. Okay, but because you push more mass to be nearer to the axis of rotation, therefore your moment of inertia will decrease. Your moment of inertia will decrease. If you compare to this, it decreases, then it means by it's smaller than the moment of inertia of the disk. Okay, so with that said, you will know that the smallest moment of inertia will be the sphere. Okay, that's all for question 4. Let's move on to the next question. Question 5 asks for which axis gives the largest moment of inertia for the disk. Well, okay, you can think of it simple. Okay, you can think of it with a more direct way. You see this one is the maximum distance, but you see this one is their maximum distance, and this one is their maximum distance. So this one is R. This one you can think of it as 2R. This one is also R. So for sure you see that this one has mass which is much further away compared to the other two disks. So this disk right here, you can immediately say that it has the largest moment of inertia. Okay, but between this one and this one, which one have more mass and which one is having a larger moment of inertia? This one, how do we compare? Let's draw this out to compare. Okay, so if this is my disk, okay, then I copy one more disk. This is my another disk. So if I choose my moment of inertia to be at the center, then you can think of the mass that is near the center. Let's say the mass which have a distance of r is this much. There's this much mass near the distance of r. Okay, but if you choose your axis of rotation to become here, then the distance r will probably cover this much of the mass actually. So that's a much more mass being near the axis of rotation actually. So if much more mass being near the axis of rotation, this one will have a lower or a smaller moment of inertia. So we can conclude that this one will have the smallest moment of inertia, whereas this one will be somewhere in the middle, moderate inertia. Okay, so with that said, we can conclude this question. The largest moment of inertia will be this where the axis of rotation is at the circumference. Okay, this one is at the center, this one is another kind of axis. Okay, so this here will be our answer. So that's the two questions that I discussed for chapter 8 revision quiz set 3. That's all. Thank you very much.